Welcome to Wetland Design. So when we're talking about wetland design, we're talking about constructing a wetland or creating a wetland where one would not otherwise exist. So when we design a wetland, we're creating a wetland in a place that wasn't one before. You actually, when we talked about Section 404 of the Clean Water Act with mitigating all wetlands, you can't use an existing wetland. So this has to go in a place where there was not a wetland. It can be used to treat wastewater. It can be used for an ecological function. There's many reasons why you would design a wetland, but it's created to meet some sort of ecological or human need. There's many types of constructed wetlands. The basic ones are a surface flow wetland, or you also hear them described as free water surface, so FWS. And basically, as that means, it means the water is, you can see the water. It's free water surface. A subsurface flow is also called a rock reed system, where basically you do not see the water. The water is flowing underneath the surface of the wetland, and the plants do emerge out, but it flows through a rock subsurface, and often you'll have reed plants that are then emerging out. There's also stormwater wetlands. So these are wetlands that are designed to hold water and then infiltrate it slowly. And then we have vertical flow systems. These are a type of subsurface flow, but instead of it flowing just kind of through horizontally through the system, these are going to flow vertically down through the system. So it creates oxygenated and anoxic or without oxygen zones. So if we start with our subsurface flow wetland, again, it's an emergent macrophyte treatment system. So we have plants that are doing a lot of the treatment and microbes. And again, the water's coming onto the surface and then it's leaving via surface flow. So the first thing when you construct a subsurface wetland is you're going to need some sort of liner. So the liner can be a clay liner, but you need to, again, if it's a clay liner, you need to ensure that the liner is kept wet because you don't want it drying out and cracking in the clay. Or you can use a plastic or geomembrane liner. So again, especially if you're putting in wastewater, you're treating it, that you don't get infiltration. Now, you may not want a liner. You may actually, if you're doing a surface wetland for ecological functions, we may want the water to infiltrate. But again, if we're doing some sort of treatment system, then we might need a liner in there. Commonly to build these systems, the levees are basically pushed up from the side and the volume is partly dug out. And again, you might create some mounds or some undulations in the system so that you have variations in the water and so that you have emergent vegetation and maybe some standing vegetation as well. So the hydraulic loading, the water coming into the wetland, can be controlled using an orifice where you basically have a tube and you drill a hole in the middle. And so it can come through a point flow, or you can build a manifold. So a manifold is going to be going across, and then you're going to have holes that going across the manifold. So instead of it coming in one point of the wetland, it might go across the whole, in horizontal flow through the wetland across a horizontal distance. In terms of the outflow, the level of the outflow, so the bottom of this pipe is going to control how much volume is in your wetland. And so for your outflow, you may actually have some river walks to protect from roots getting in, and you might actually put like a cheesecloth even so that you don't have roots coming into your pipes. But basically you're going to have the water coming into this pipe, and then again, the elevation that's going to come up here. So it's not going to discharge here. Otherwise your water would just flow right through, So it's not like a bathtub. It actually has to come here where it's coming in, it's flowing through, and then it's going to come out based on the height of this pipe. The emergent wetland plants fill a variety of roles. They promote microbial degradation of the waste. They also uptake nutrients and contaminants the plants to themselves. They also create microsites within the root zones. So there's specialized structures in wetland plants called parenchyma, and basically it allows oxygen to reach into the rhizosphere And so these plant stems, they can provide not only for oxygen to leach down into the root zones, again, minimal oxygen, these are still anaerobic zones, but it creates these aerobic microsites for the oxygen to reach these root zones, as well as the stems provide colonization in for plants. The actual, as you build these emergent plants, the stems can actually help promote uniform flow so you don't have preferential flow patterns through your wetlands. They can also shade the water, which is actually good because we don't want a lot of algal growth and phytoplankton growth, because that can be a source of additional organic matter, additional BOD, because when it degrades, then you're going to have more organic matter coming into your system. They can also inhibit wind mixing. And again, that wind mixing is going to create less uniform flow and maybe create a preferential flow pattern. And so having a lot of emergent vegetation is going to help. So if we think about the plants that you might have duckweed and other floating aquatics. You're going to have the emergent plants as well. And then you're going to have detritus from the plants. And so within this, you're going to have your particular BOD, your organic matter. You're going to have organic based phosphorus and nitrogen in the detritus and settled total suspended solids. You might have metals and other things that are suspended here. Again, you're going to have a low dissolved oxygen. It's going to be anoxic. And you're going to want this to be as vegetated as possible. Again, you're going to remove through flocculation, sedimentation, absorption, and anaerobic reactions are going to be your primary removal mechanisms. You're going to get some removal through some oxygenation through atmospheric radiation at the surface, not a lot, but some. And then again, some oxygen coming from the roots of special wetlands plants. You're going to get some UV radiation, which might help with decreasing coliforms. And then you also might have submerged vegetation in addition to emergent vegetation. And then you might even have an open water zone. And in that open water, you're going to get more pathogen kill, and you might get a little bit of atmospheric aeration to get some aerobic treatment. The advantages, again, you can see the water, and so it's really good for outreach. It's good for recreation, walking trails, birding. It actually creates habitat in terms of wildlife habitat, increasing biodiversity and nursery for aquatic species. And it can provide other services like flood control and storm surge, because the water is at the surface, and depending on how it's built, it may be able to hold some of that water in addition to other benefits that it has. Potential risks, again, with surface flow wetlands, we are worried about creating mosquito breeding grounds, risk of West Nile virus, malaria, and other diseases. But there are things you can do to try to help control mosquitoes. You can actually kind of build it with steep concrete slopes with deeper bottoms. And you can also put mosquito fish that actually, gambusa, that actually can eat some of the larvae. And you can also do non-mosquito conducive plants. So for example, like floating lettuce tends to actually have little pockets of water in there, and the mosquitoes can breathe in there. So you want to think about what type of plants you have, both emergent and submergent. And then also there are mosquito specific bacteria that can break down the larvae. In terms of subsurface wetland, here we're not going to see the water at all. So we're not going to get a lot of the stormwater surge control. We're not going to get a lot as many wildlife habitat benefits, because all the water is actually going to be below the surface. So we're going to dig out here. We're going to plant our plants, and we're going to have gravel through this entire media. And we're going to have our plant roots within that gravel. And then it's going to move horizontally through. And so here our height is controlled by the height of this pipe. So it's actually our pipe's going to be up here, and then it's going to come up and kind of spill over. And that'll be the height of your water. So it's filled with, again, river stones or gravel. You don't want to use fine sand because you want actually void spaces. The treatment volume is actually, you want the water to be able to move through, and you want a lot of water to be there. So the treatment volume is actually the space between the stones. So you design for that void volume, because that's how much water can go through, because the stones are going to take up space. So it's the void volume is the space for your water to go through. But the stones are actually really good in terms of providing surface area, colonizing surface for microorganisms, as well as you have those root zones as well, which are an important part of treatment, both in subsurface and surface wetlands. And so you might have, for example, if this was a wastewater system, you might have a septic tank, and then which you'll get a lot of settling of solids, because you don't want, for subsurface wetlands, you don't want a lot of solids going into your system. So if you have a lot of solids, it would be better to have a free surface wetland where you can actually have the solids settle out in a zone, because if there's a lot of solids going through your subsurface wetland, they're going to clog, and then you won't have that void volume that's so important. So you might actually have a settling tank, and then you would have your subsurface here. Again, especially when we're treating wastewater, we may want it to be subsurface for environmental protection, and so that we don't have coliforms introduced into the environment. And you may have it where some of these are zero discharge, or you may have other discharge, and then you could even then after that put into your leach field and have infiltration. If you see water in the surface of a subsurface wetland, then that's a good indication of plugging or some clogging or an overload problem. You can actually step feed these systems. So your wastewater inflow, you can have it at more than one point. So here we have a step feeding system where we have actually wastewater coming in here, also coming in here, and also coming in here. And so that we can make sure that we get a more uniform flow as we go through and utilize more of the surface area, the length times the width, by just spending it along a greater portion of the wetland. Instead of just having it come here, you can have it come in various steps, which can avoid kind of clogging of media, of having one input, and could have some better aeration. So if we have a subsurface with vertical flow, instead of the water coming in here and then exiting out at the top, exiting out at the top, if we have it with vertical flow, then it's actually going to exit out of the bottom. So it actually comes in. So you actually have an aerobic zone. So water isn't filled all the way up at the top. It actually has an aerobic zone, and then it meets, and the water is actually only in this bottom part. And so then you have your anaerobic zone, and then you have your discharge at a lower elevation. So it actually is, it's less time that it's in the system, but it has both an aerobic and anaerobic point, but there's less treatment volume there. So stormwater wetlands are going to differ from surface and subsurface wetland, and that the loading isn't uniform or continuous. So it's not something that's being pumped into every day. It's not something we're necessarily using at the back of a wastewater treatment or a back of a septic system. So these are going to be shallow detention ponds that are kind of used that first flush for treating runoff. So they may be dry during parts of the year, but then when they do have kind of that first flush, which has a lot of contaminants and other things that can go into the wetland, fill that up and treat it during that time. So if we think about a hydrograph, if we think about the flow, the cubic feet per second, again, we're not going to have a lot of rain, and then all of a sudden it comes and we just have this huge flow come out. So if we're able to route that to a wetland or a wetland pond, the idea is that it'll slowly fill up, and then it'll slowly over hours let that water come through, versus a conveyance pipe, which again can cause a lot of erosion and damage to our streams. So the idea is that we figure out this design storm and how big we need to make our wetland, so that a large magnitude of it can then settle into our wetland and infiltrate and slowly discharge. So there's a lot of wetlands are built for municipal treatment, but not always. Actually, one of the biggest builder of wetlands is actually Ducks Unlimited, more for habitat. But again, a lot of municipalities do build wetlands for municipal wastewater. And so this would be the tertiary treatment, or sometimes even the secondary. But usually it's after settling of solids, and then it would go through a wetland. So in this manual, it has everything you need to know about designing them and about the equations that you need to use. But I did want to point out some of these myths that are in this manual. And so basically they're saying that these are things that we need to consider when we're designing wetlands, because there's not always information out there that it makes it easy to design. The myth number one is that wetland design's easy to do with published equations. So yes, we're going to go over published equations, and there are published equations, but you need to be careful. And one of the reasons is whenever we're studying wetlands, I may get a influent point on September 1st. My effluent point that I also get on September 1st is not the same as that influent wastewater. So if we had a big plug of pollution that came through, that's going to show up in my effluent, for example. But if it already went through or it's already in the wetland, it's not necessarily going to show up my influent. So it's hard to pair those data. And even if I know that I have about a 2-week retention time, and so I take samples every 2 weeks with the idea that my effluent from 2 weeks later can match with my influent, we don't really know the exact retention time, and not all those particles have the exact same retention time. And there's also rain, especially if it's a surface wetland, how much rain happened between those 2 weeks? Was there dilution from that rainwater? And so it's really hard to pair up these effluent and influent data with these grab samples that we might take. And it's hard to get that valuable retention time data. Also, often with these equations, things like temperature, precipitation aren't included. And so the other thing we need to worry about is often cleaner wastewater effluent. So we may be putting wastewater in with only 1 milligram per liter nitrogen. And then I'm using the same equation when I have 100 milligrams per liter of nitrogen or 20 milligrams per liter of nitrogen. And we may not be getting those same removal rates with that higher concentration. So again, the misconception is that wetland design's been really well characterized by published design questions, but in reality, they're complex systems in terms of biology, hydraulics, and water chemistry. And there's a lack of quality data of sufficient detail, both temporally and spatially, on full-scale constructed wetlands. Due to this lack of data, we've been forced to derive design parameters by aggregating performance data from a variety of wetlands, which can lead to uncertainty about the validity of these parameters. The myth too is that they have ample aerobic and anaerobic zones. And while plants can get through fermatophores and through these kind of like straws in their stems, and they can get plant oxygen to their roots, and some is released into the environment. But usually the oxygen demand of this water overwhelms the small addition of oxygen to the water column through all the detritus that is there, the algae, as well as if you're putting wastewater in. So the misconception is that they have aerobic as well as anaerobic treatment zones. It's probably the most common misconception is the ability of this emergent wetlands to transfer oxygen to the roots. And so emergent plants are uniquely suited to the anaerobic environment of wetlands because they can move oxygen from the atmosphere to their roots. And research has shown that some of this oxygen leak from the roots goes to the surrounding soil. So this phenomenon in early work with national constructed wetlands that treated wastewater with a low oxygen demand has led to the assumption that there's significant aerobic microsites within all wetland systems. But again, this doesn't always happen within all systems. So we need to be careful about the type of waste that comes in. So if we know we're getting a lot of ammonia coming in, then we may not get ample treatment because we need aerobic zones for nitrification to happen before denitrification can happen in our ample anaerobic zones. And that goes to the next one, that they can remove significant amounts of nitrogen. So again, the misconception is that they can remove this nitrogen related to this misconception about the availability of oxygen in constructed wetlands, and therefore their ability to remove nitrogen. Harvesting removes about 20% of the influent nitrogen studies have shown at conventional loading rates, which leaves nitrification, denitrification, which is how we remove nitrogen in wastewater treatment plants, as the primary removal mechanisms. So again, if ammonia is, if we aren't going to get nitrification of ammonia unless we have ample open water, vertical zones, or other designed oxygen inputs. Otherwise, they may be used in construction with other aerobic treatment practices that can nitrify. So you may have a trickling filter first and then go into your subsurface wetland. And myth number 4 is that they can remove significant amounts of phosphorus. Phosphorus removal is limited to seasonal uptake by plants, which is not only minor compared to the phosphorus load in a lot of municipal treatment, but it's also negated by, again, these plants. They're gonna unless they're harvested, they might their leaves fall down. That phosphorus is still in the leaves, and that falls down into the water. Again, you may get some absorption, but this absorption is limited in terms of how many absorption sites that we have. So in many tertiary wetland plants with low influent concentrations, the removal of 1 milligram of P is reported as a large percent removal, but that's not that much. And so when we looked at newly constructed wetlands, we also get a lot of phosphorus removal due to a lot of microsites there for phosphorus absorption. And new plants are going to take up more phosphorus than mature wetlands. And so we need to just be clear about what kind of phosphorus absorption capacity we're going to have over time. Doesn't mean it doesn't happen. We just need to plan for it. So when we do design wetlands, we're looking at a hydraulic budget first. And so we're looking at our Q1, which is our inflow, and our concentration of whatever it is, the organic matter, the nitrogen, the phosphorus, whatever's coming in. We're going to have the flow and the concentration. We're going to think about evaporation and precipitation. And then we have our area of our wetland, and then we'll think about our outflow, the rate of outflow, and the concentration in that outflow. So when we just think about hydrology, we're going to have our QN minus our QO, plus precipitation minus evaporation is going to be our equation that we're going to use, which is a reaction of the volume of water in time. Again, in this example, groundwater infiltration is excluded because this is assuming there's a liner. If there's not a liner, then you also need to account for groundwater infiltration in your hydraulic budget. So for evapotranspiration, we're going to use this equation that again is a function of temperature, the daily temperature, the number of days, and it's going to vary month to month in terms of how much evaporation that we get. If we're talking about organic removal, again, we want that loading to be distributed over a significant portion and not at a single point if we can. And again, the depth should be about 24 inches or less to assume that we are going to have some, if we have a lot of organic matter coming in, so that we do get some aerobic oxygenation. We might even need to do partial recirculation in the summer months to overcome the evapotranspiration loss to maintain design flow rates. Again, we can control it by that step feed distribution, again, having it various throughout, or recycling of the discharge. A loading rate of about 112 kilograms BOD per hectare per day is a typical upper loading rate that we don't want to go over. And again, that oxygen, we can transfer at about 5 to 10 grams per day. It's not a lot per meter squared of, per surface area, meter squared of wetland surface. And so it can be lower depending on the vegetation cover that we have. So organic matter BOD removal in a wetland has been described by a forced order model. So we have our concentration in the influent of BOD divided by our concentration, or in the effluent, excuse me, divided by our concentration in the influent, what's coming in, equals an exponent of, again, e to the negative k times t. Both of those are up in the exponent. So e taken to the negative k times t, with our negative k being the temperature dependent forced order reaction rate. That's our k, that's our rate. And then the t being the hydraulic retention time in days. And so our reaction rate is based on the temperature. So our KT, you basically have the reaction rate that you would get from a book for whatever we're looking at, the concentration that we're looking at. And then you have your reaction rate that you're going to get at 20, and then you're going to do a temperature rate constant so that you can figure out, well, at 20 degrees Celsius, this is the reaction rate I get, but in the summer, I'm going to have this reaction rate, and in the winter, I'm going to have this reaction rate. And so your reaction rate is going to change based on the actual temperature conditions. We also need to calculate the area needed. And so our area, again, is going to be based on the flow times, again, the natural log, because before it was E, the opposite of our E is our natural log. So we're going to have the flow times the natural log of the concentration coming in minus the concentration going out divided by the K BOD. And again, it being temperature dependent. So for this example, for example, it's 0.1 at 20 degrees, but you would adjust that based on your degrees. To figure out your hydraulic retention time, that's going to be your length times your width times your depth divided by your flow rate. Okay, so it's you know, meters of length, meters of width, meters of depth divided by the cubic foot per meter cubed that's coming in, for example, the amount of water coming in. For retention time for a subsurface wetland, though, it's going to be a function of the porosity which is the remaining volume of the cross-sectional area. So the volumes is the void volume, and the volume are the voids that are there. So depending on the type of media that you have, your porosity is going to be different. So with gravelly sand, we're going to have much less porosity, less void volume than if we have medium or coarse sand. And so that's going to affect both our hydraulic conductivity, how it moves through the system, as well as our reaction rate, our K value. So we can combine these equations to get our temperature times our depth, times our area, times our porosity divided by our flow rate to get our detention, the retention time in the wetland. Again, we can also look at the slope. Again, depending on if we have a slope with our wetland, if it's a vertical flow wetland, then we need to take into account that as well. And then you can combine them all to get this really big equation. And that basically tells us our concentration. So if we know our concentration coming in, we can then calculate our concentration coming out using this equation. Area, KT, area, 1.75, length times width times depth times porosity divided by flow. All right, thank you.